Okay. Hello, everyone. And let me first start by thanking the organizers of this very interesting workshop for allowing me to present my latest work on limiting curvature in the very early universe. Let me start with a little bit of an introduction and some motivation. This talk will be mostly about singularities, and in particular, singularity resolution in cosmology. We all know that in general relativity, with some effective matter that satisfies the usual null energy condition, then we're inevitably going to run into singularities. That's even true in inflationary cosmology, where the space-time is often past and complete. And so if we want to talk about what could have happened before inflation, or in some alternatives to inflation, where one could have either a bounce or something like a loitering phase in a genesis scenario, then we have to address the question of singularity resolution, and in particular, we have to violate the null energy condition. This can be done either with some quantum fields or by modifying the theory of gravity, or actually having a full theory of quantum gravity. And there are indications that this might not be too crazy in a sense. Already just with fields from the standard model of particle physics, there are examples of traversable wormholes where the null energy condition is certainly violated. And in known quantum field theories, what is usually satisfied is something more like an averaged energy condition that would in principle allow the violation of the classical null energy condition for some short period of time. Additionally, there's motivation coming from quantum gravity, such as string theory, where we certainly expect curvature corrections, such as alpha prime corrections. These corrections might not imply singularity resolution, but at least in principle could allow for it. And furthermore, in other theories of quantum gravity, there's often some fundamental length scale beyond which the space-time continuum doesn't make any sense. It cannot be probed. And so in these theories, singularities do not exist. However, if you want to build an effective theory of gravity and matter that resolves singularities, it's often kind of difficult. A very popular avenue is to consider a very generic theory of scalar tensor gravity, such as Horndeski theory, which has many free functions. And there are many examples where one can choose these functions such that we have a well-defined non-singular cosmology throughout time. But the problem with that is when we look at cosmological perturbations, so inhomogeneities beyond the background, we often run into instabilities such as ghosts or gradient instabilities. And in fact, there are indications that there's a no-go theorem that would imply that it's simply impossible to have a stable non-singular cosmology within Horndeski theory. There might be a few ways of evading the no-go theorem, and there are examples of that. But in many cases, this is done at some cost. In particular, it often leads to issues of strong coupling. Now, today I want to talk about a slightly different approach than to singularity resolution, which is that of limiting curvature. The idea there is to approach the problem from a slightly more brute force approach, if you will, in the sense that we want to bound curvature already at the level of the action by having some constraints on curvature. And so this idea was developed in the 80s and early 90s. And in particular here, I'm presenting it in the way it was written by Mukhanov and Brandenberger in the early 90s, where the idea is to start with the usual Einstein-Hilbert term and then introduce a number of auxiliary fields chi that multiply some curvature invariant functions I that depend on the Riemann tensor, the metric, and covariant derivatives thereof, and then with a potential for all of these auxiliary fields. Then by varying the action with respect to these fields, we obtain a set of constraint equations such that if the derivatives of the potential is bounded, then so will be all of these curvature invariant functions. And so that way we ensure that these curvature invariants do not blow up. Specifically, you could work with two of these functions, I1 and I2, built with the Ricci tensor and the Ricci scalar in this particular form, such that in FRW, this is proportional to Hubble dot, and I2 here is proportional to Hubble squared. And clearly, if you bound these quantities, indeed, you can obtain a non-singular cosmological background. But when we revisited that in 2017, we found that when you look at perturbations, you immediately run into severe instabilities. And typically, it's hard to write down a theory that way that will be free of singularities. So let me present a slightly different approach to limiting curvature, which is that of mimetic gravity, as first studied by Chemsedy and Mukhanov. The idea here is to introduce a new scalar field, phi, which is constrained by this equation here. And to do so, one can introduce a Lagrange multiplier lambda in this way. And then one way of writing the theory is to introduce another auxiliary field chi that multiplies the D'Alembertian of phi with a potential. Then, by varying with respect to chi, we get this constraint equation, box phi is equal to the derivative of the potential, and that's just the limiting curvature constraint. To connect this with the more common way of seeing mimetic gravity, we can solve this for chi as a function of box phi, and then we can define this function f of box phi such that upon substitution in the Lagrangian, we obtain only an expression in terms of phi. That's usually how we see mimetic gravity written down. Now, to see how this allows for non-singular cosmology, we can look at an FRW background where the scalar fields could just be our clock, just time, and then this is going to satisfy the constraint for phi. And then box phi is simply proportional to Hubble. And so bounding the derivative of the potential ensures that we're bounding the Hubble parameter. And indeed, as studied by Chemsedy, Mukhanov, and others, this can allow you to write down a non-singular cosmology. But yet, when you look at perturbations, once again, you typically run into instabilities, particularly gradient instabilities. Although it's doing better than the original limiting curvature theory, in that you have only these gradient instabilities, no ghosts and no Strugatsky instability. Yet, also, if you look beyond FRW, if you look at an anisotropic spacetime like Bianchi, then you can still have instances where you have divergences, and so not all curvature invariants would be bounded. Nevertheless, this gives us some intuition for what to look at that could be a better limiting curvature theory. And that leads me to Cuscuton gravity, which I'll introduce here. The setup is to have, again, just GR and a scalar field, which this time we want to be fully non-dynamical on a cosmological background. And this was first implemented by Abshorty within a k-essence theory, where the idea is to have a general function p of x and phi for the scalar field, where x is the kinetic term for phi. And then the equation of motion for the scalar field in FRW is given as follows. And if you want this to be non-dynamical, you want the coefficient of the phi double dot term to vanish. If you impose this, then the function p of x and phi has to take this particular form. And usually by rescaling phi, we write down this Cuscuton Lagrangian simply as some new mass scale multiplying the square root of the kinetic term and then with a potential. Then the equation of motion for the scalar field really becomes just a constraint equation. It's non-dynamical. And we see from it that it's in the limiting curvature form. Indeed, it's simply the Hubble parameter, which is constrained by the derivative of the potential. And in fact, the curvature that is bounded here is really the trace of the extrinsic curvature. So the full constraint equation here can be written as follows, where the trace of the extrinsic curvature is given by the divergence of this vector field u mu, which is the normal unit vector to a constant phi hypersurface. And because this allows it allows bounding the trace of the extrinsic curvature, it allows one to build a non-singular cosmology once again. What's interesting about the Cuscuton, and so particular, is that this time, if you look at perturbations, here just for gravity and the Cuscuton field, no other matter, then your scalar perturbations are not going to propagate at all. Indeed, you can expand the scalar action up to second order, and you find that the coefficient of the kinetic term simply vanishes by definition of the Cuscuton. Also, the Cuscuton has many interesting properties. I'm just listing a few here without going to any particular details, but just to name them, it was found that if you're in a flat space, then the Cuscuton doesn't form any caustic singularity. Also, it has a particular interpretation as coming from a five-dimensional brane theory. And also, it was found fairly recently that it has many new symmetries beyond the usual Poincaré symmetry. All of this led us to think of a unifying approach to limiting curvature. And specifically, we had in mind limiting extrinsic curvature in the same way that Cuscuton theory is bounding trace of the extrinsic curvature. And so to define this in the same way that Mukhanov and Brandenberger studied it, we can introduce a set of auxiliary fields chi, multiplying some curvature invariant functions I, but this time these functions would be only functions of the extrinsic curvature k, the induced metric on a hypersurface sigma, and spatial derivatives on that hypersurface. Then we have to specify our foliation, sigma t in this case, by the unit normal vector n mu, by introducing a new field. And this could be either a scalar field, and then the unit normal vector becomes the gradient of that field, or it could just be a new vector field. And in each cases, we have to impose the constraint that the normal vector is normalized to unity and is time-like. One example of this theory would be to set a single curvature invariant function I1 to be the trace of the extrinsic curvature, which inevitably would just be 3 times the Hubble parameter. And we can write this down either with the scalar field phi or with the vector field a mu. And this first term here ensures that we have this constraint satisfied. And then the terms after are the auxiliary field chi and the curvature invariant function and the potential for the field chi. And I'm claiming that this first way of writing down the theory is just mimetic gravity, whereas the second one is just Cuscuton gravity. For the first one, we sort of saw it already. If you have the Legendre transformation f of box phi given by this, then this is typically the way we see mimetic gravity written down. For the Cuscuton, it's a little less obvious, but if you get the equation of motion for the vector field and you solve it together with the constraint for a mu, you get the solution for lambda and for a mu. And upon substitution in the Lagrangian, you get the typical expression for Cuscuton gravity, namely just the square root of the kinetic term and potential. So it looks like mimetic gravity and the Cuscuton are very similar from one another, and in fact can be written in pretty much the same form in this general class of limiting extrinsic curvature theories. Now, however, there's a key difference between the two. And to see this, let's consider again the equation of motion for the vector field a mu in the case of the Cuscuton. We can solve this for lambda as follows. And we can do a similar thing for the scalar field phi in the case of mimetic gravity. In this case, the equation of motion has an additional derivative simply because we see that the scalar field phi enters with a derivative in the action. And so when one solves for lambda here, we get an additional constant of integration, if you will, u mu here, which does not appear in the case of the Cuscuton. And in fact, u mu here really is constant in the sense that its divergence vanishes. And to see what physical implication this has, we can look at this constraint in FRW, and we see that for u0, this is solved as follows. u0 will scale as a to the minus 3, where a is the scale factor. And u0 then enters the Freeman equations as some new energy density, and therefore it behaves just like dust. And this was the idea behind mimetic dark matter when it was originally proposed. But in the Cuscuton, one does not have this term, and one does not have this dust-like matter, additional matter. And that's one way to see that, in fact, the Cuscuton has one fewer degree of freedom than mimetic gravity. And then when one considers a non-singular cosmology, it will turn out that it's better in the sense that often it will lead to more stable solutions. And we can look at one solution of that specifically. In this case, Cuscuton with matter. We can take the usual Cuscuton field and add some matter, in this case, just a massless scalar field. Then the Freeman equation takes this form where this new term right here is a contribution from the Cuscuton field. And in particular, when the second derivative of the potential lies in this range for a particular time interval, we find that the time derivative of the Hubble parameter is greater than 0, meaning that we're effectively violating the null energy condition. So with that, we can build a non-singular cosmology and look at perturbations on top. And it was found that there are no ghosts and no great instabilities throughout time, already back in 2018. And when we revisited that, we found, in fact, that there's some interesting behavior happening. In particular, when one is close to the bounce, when h is close to 0, one can look at perturbations in the scalar sector in the UV for large k modes. And from this, we can easily read off the sound speed squared for the fluctuations. And because we're in the bounce phase where h dot is greater than 0, we immediately see that the sound speed is greater than the speed of light. In particular, if we define the second derivative of the potential at the bounce by this new mass parameter, we can write down expressions for the sound speed, say here first in the IR limit as follows, and then this can safely lie in the range from 0 to 1, provided this mass parameter lives in this range. And then in the UV, the corresponding sound speed will necessarily be in the range of 1 to 10. So it looks like one cannot avoid these superluminalities in that case. Just to visualize this a little better, if we pick a particular value of the mass parameter there, we can plot the sound speed versus time in the bounce phase, where 0 would correspond to the bounce point, and versus the wave number k of the fluctuations in the UV. And we see there that we asymptote CS equal to 1 after and before the bounce. And during the bounce, there will always be some periods of time where the sound speed grows larger than 1, but nevertheless bounded, in this case, at most 10. So it looks like we have superluminality, but nevertheless, we know that this is not an issue with respect to causality. And in fact, there are well-known examples in effective field theories where mild superluminalities occur. Still, a question that remains unanswered at this point is whether this, as viewed as an effective field theory, is truly valid, and in particular, whether it is safe with respect to strong coupling. And at first sight, perhaps it is, in the sense that it looks like the sound speed can remain far away from 0, and there's a very well-defined range in parameter space where we have solutions throughout time where the sound speed is not close to 0. But nevertheless, one would have to do a more refined analysis to answer this question. Now, let me talk about another application of limiting extrinsic curvature, which is the case of bounded anisotropies. So I'm recalling here the general expression for this class of theories. And this time we could consider two curvature invariant functions, I1 and I2. I1 given by the trace of the extrinsic curvature squared, and I2 given by the contraction of k mu minus a third k squared. If you work with nu given by simply a vector field, as in the Cuscuton-like case, then this Lagrangian would look as follows. Now, this is interesting because if we look at not FRW, but rather an anisotropic spacetime, an anisotropic background, such as Bianchi-1, then, well, first I1 will be proportional to Hubble squared. So by bounding the derivative of the potential, we can bound Hubble again. But this time, I2 is given by this anisotropy parameter sigma, which is simply defined as by these time derivatives of the beta parameters that characterize the anisotropies. And it is this time this anisotropy parameter will also be bounded provided the derivative of the potential is bounded. So not only can we bound the typical FRW background, we can also bound the anisotropies. Now to see this at play, let's
Jerome, sorry, there is a question from Sriram, if you could take that in the chat. Sriram, if you could unmute yourself and you can ask it.
Jerome, does XML lead to a symmetric bounds? Is there where dot h equals? Okay. Let me answer the second question first. When dot h is equal to 0, already CS is going to 1. This is already far from the regime where the Hubble parameter crosses 0. So just in this, where is it? Yeah, just in this example here, one would exit the bounce phase and already CS would go to 1. And in fact, it has to go to 1 asymptotically because outside of the bounce, the Cuscuton becomes negligible, and we simply had a massless scalar as the additional matter. And for a massless scalar, we know that the sound speed is 1. So when dot h is 0, no, CS would be 1. Whether it's symmetric, well, it depends on the form of the potential, really. In this example, it is because of the choice of the potential. But in general, there could be, one could construct a non-symmetric bounce, certainly. And I see there's another question that I can answer right away. Why you call CS squared causal? Right. This has to do with, this was studied, yeah, I'm putting a couple of references here in 2006, 2007. Essentially, when you have a sound speed greater than 1, what you can do is define an effective metric such that you're simply changing the angle of your light cone. And this newly defined light cone will determine how causality works in the space-time. So in that sense, as long as the sound speed doesn't go to infinity, you can't have infinite propagation of information, for instance, or you can't have achronal events. Well, you can't have propagation of information in an achronal way. Right, I was discussing this Taylor model where we're bounding anisotropies. So consider vacuum for simplicity in that case. And let's look at the equation of motion for the anisotropies. This is solved easily, and we see that the energy density in these anisotropies goes as the typical 1 over a to the power of 6, except we have this new term, 1 plus 2 chi2 squared, that is not there usually in GR. And in fact, in this theory, because we're bounding sigma, we're really bounding the energy density in anisotropies. And one can set up a model where the energy density in anisotropies goes to a constant at early times. So essentially, chi2 will scale as a to the minus 3 at early times. Specifically, you can write down a potential for this as follows, where mu would be the new energy scale at which this limiting behavior occurs. As we can see, then H will tend to mu, and sigma will tend to mu at early times, whereas one recovers GR at late times. To see what the spacetime is really doing there, we can write the metric as t goes to minus infinity as follows, which is just like de Sitter, except that the Hubble parameter in the x and y directions versus the z direction are different. So it's like anisotropic de Sitter. And here's just a figure where we see that it's explicitly the blue curve and the orange curve for h squared and sigma squared tend to a constant as time goes to minus infinity, whereas they decay in the typical way for GR and go to 0 at late times, in this case because we are in vacuum. So now let's look at perturbations in that case briefly. Since we're in vacuum, we have only 2 degrees of freedom. They're just like the usual polarization states of gravitational waves in FRW, except because we're in a Bianchi-1 spacetime here, those won't be tensor modes, but rather it'll be one vector mode and one scalar mode. Particularly, we could consider beta minus to be 0 and just consider beta plus, and because of the rotational symmetry, and then we would only have to consider the k direction, the y direction and the z direction. Then we can look at the vector perturbations first. We eliminate all the gauge degrees of freedom, and in the end, we're left with a single propagating mode, h cross. And we can read from the coefficient of the kinetic term and the coefficient of the gradient term by asking those to be positive, that there are no ghosts and no gradient instability as long as 1 plus 2 chi2 is greater than 0, which precisely happens in the example showed earlier, because chi2 was always positive. Now, if we look at scalar perturbations, again with the same methodology, the single degree freedom that is propagating in the end is the H plus mode, and by reading the sign of the gradient term, there's no gradient instability. But this time, the coefficient of the kinetic term is rather complicated. And let me simply point out that we found that this is positive, but only if the co-moving wave number in the y and z directions are of the same order, give or take a couple of orders of magnitude. Essentially, if these wave numbers are too different from one another, because physically these wave numbers grow in one direction and shrink in another direction, it turns out that this leads to an instability otherwise, and specifically a ghost instability. So let me summarize what we've learned with this. We saw that we know that there exists a wide class of scalar tensor theories, and in fact can be sort of unified in spatially covariant theories. But a subclass of those can be written as limiting extrinsic curvature theories. And we found that mimetic gravity and the Cuscuton simply are subclasses of these theories. And in particular, they admit FRW non-singular backgrounds, as we knew, but also they can be generalized to build non-singular anisotropic cosmologies. In the case of the Cuscuton, we confirmed that the perturbations are stable across time, at least at the level of classical, at the classical level, and for linear perturbations. So under these assumptions, we're evading the typical no-go of Hornetsky theory. We found that one can have a sound speed of the order of unity throughout time, except close to the bounce, where it looks like superluminality is unavoidable. And it remains to be checked whether the corresponding theory then is a valid effective theory. And that would involve computing the actual strong coupling scale. And this is ongoing work that I'm currently doing. Then one could generalize this to an extended Cuscuton. And what we found in that case is that, once again, the bounce appears to be stable. I didn't talk about this for the sake of time, but the extended Cuscuton would just be to start with a more general theory at first, say Horndeski rather than k-essence, and then impose once again that this field is non-dynamical for the background and the perturbations. Finally, we also are in order to understand how the perturbations evolve through a bounce with this theory, because it is stable at the classical and linear level. And so far, what we found is that, at least for modes on super Hubble scales, perturbations remain bounded. They can grow, but only by some limited amount. Now, finally, I talked also about anisotropic spacetimes. We found non-singular solutions in Bianchi 1, at least some toy model in vacuum. So far, there seems to be still some instability, unfortunately, for this particular model, but I'm hopeful that there exists some other theories in that class that could potentially be stable, but since we only started looking into this, I don't know yet, but it's promising. So let me end here and take more questions.
Thanks, Jerome. So if you have any questions, please either raise hand or type on the chat box, and I would request you to unmute yourself and ask. I think Patrick has a question. Professor Patrick, please unmute yourself and ask the question.
Yeah. So you mentioned that indeed you are managing to limit the expansion anisotropy in the Bianchi 1 case, just as you are limiting the curvature. But what about the, do you think the same kind of thing will apply, the same kind of constraint will apply to the curvature anisotropy, like in Bianchi 9, and that you will be able to avoid in this kind of theory, you will be able to avoid the BKL instability?
Right. That's a good question. For the, one could study it and one would have to check for a given theory. Let me just say that, where is this? Sorry, here. Let me just say that at this level here, where there are two curvature invariants that are bounded, k squared and this contraction of k mu nu and k squared, I don't think so for Bianchi 9 rather. But one could add a third curvature invariant, say I3, which would be say the three-dimensional Ricci curvature, and then given a potential that is whose derivative is bounded, then this could also be bounded. Then the theory is more complicated, but nevertheless, it seems possible at first.
Thank you.
Next question is from Professor Brandenberger. Yeah, please.
I'm sorry, let Robert ask.
Yes. So Robert's question, why doesn't one see... Go ahead.
Yeah. So I was wondering why this instability, which you see in the anisotropic case, why does it freeze out in the isotropic case?
Well, first, let me mention that the theory here with this additional curvature invariant, it was the first time that this was studied even, well, in Bianchi 1, but not even in FRW. So we didn't know whether this was stable in FRW or not. Now, it looks like it's unstable in Bianchi 1, but I didn't talk about the FRW limit in that case. And it's, well, from what I have here, I don't recall the answer, whether the stability, yeah, I don't recall what's happening with stability in the FRW limit here. But I can just point out that there are well-known cases where one has a stable FRW cosmology, but nevertheless an unstable Bianchi 1, for instance, anisotropic spacetime. This happens, for instance, in the theories of F of R and Gauss-Bonnet, where you have a certain number of degrees of freedom in FRW, but yet when you look at a Bianchi 1, then there's a new degree of freedom that appears and it's a ghost. So yeah, the FRW limit is sometimes kind of tricky, and then you can lose some information about what's happening. So let me just say that here it's not clear to me. I don't recall what's the FRW limit, and but I could tell you later.
Thanks.
Okay, the next question is from Sriram. Please unmute yourself and ask. Yeah, sure, please.
Sure. Thank you. Jerome, you mentioned that the curvature perturbations grow on super Hubble scales prior to the bounds. Do they settle once expansion sets in?
Yeah, just to be clear, what I'm saying is that they can grow during the bounce. Yeah, prior to the bounce, indeed, depending on the model, if it's matter dominated, we know that they are growing. Then the question is, how do they evolve through the bounce? And typically, if the bounce is fairly short, then we don't expect much evolution, but one still has to check. And what we find is that there is some possible amplification, but not so much. It is certainly bounded. I have some additional slides if you want to see. Yeah. So if one looks at the super Hubble limit, then that's a typical equation of motion for the curvature perturbations. And there's the typical constant solution and a time-dependent one. And whether this time-dependent solution is growing or decaying depends on the evolution of the variable z and the scale factor. Z is, I didn't define it here, but it relates to it's the variable that then allows you to write down the canonically normalized perturbation variable in the second order perturbation. And in the case of, say, a constant equation of state, this would simply be proportional to the scale factor. So we see that how much zeta can grow is really bounded by how much the scale factor evolves during the bounce and the duration of this bounce phase. Now, in the case of the Cuscuton, we don't have really a constant equation of state. There's some complicated time dependence into this, and that's the expression for z squared. Nevertheless, when we studied that, we can write down an upper bound how much zeta can grow, and it's essentially the same expression as before. It depends on how much the scale factor changes and the time duration of the bounce, but there's also a factor E that depends on the parameters of the bounce itself. But upon careful analysis, these parameters are more or less order 1, or if you check all the possible limits of these parameters, it turns out that this can never be so much greater than order 1. So all in all, it looks like the maximal amplification you could receive is essentially bounded by how much the scale factor changes and the time duration of the bounce, and that's it. Now,
will you get a scale invariant spectrum in these scenarios?
Well, I'm not talking about what's generating the perturbations prior to the bounce at all. Whether it's matter contraction or product, I'm not specifying in this case. I'm just saying, given some arbitrary perturbations that have exit the Hubble radius, they're on super Hubble scales, how do they evolve the bounce? And all I'm saying is that they won't change much. Certainly in the IR, the spectrum won't change, and their amplitude won't grow more than this quantity here.
I understand.
Finally,
thank you.
After the bounce, I'm not specifying what the theory is, but no, I don't expect amplification after the bounce.
Okay.
Next question is from BC Paul. Could you please unmute yourself and ask, or maybe I just read out. He was asking, you mean bound solution is possible only in an isotropic universe? Is it not that isotropic universe with nonlinear UOS can help?
I'm not sure I fully understand the question, but no, I'm not saying that the bounce can only occur in an isotropic spacetime. The last example I was giving is a case where, well, it's not even a bounce, but it is a non-singular universe where anisotropies are bounded. which is, all I'm saying is that this is uncommon, because typically anisotropies would simply grow to infinity. And so, yeah, this was the particularity of that specific theory. And then a nonlinear equation of state, whether that can help. I'm not sure I understand what you mean by nonlinear equation of state. In all of these cases, I mean, the equation of state, again, effectively is smaller than -1. This is the whole point of saying that we're effectively violating the null energy condition. But I don't understand what you mean by nonlinear. Maybe you mean something like pressure is a constant times energy density to some power, say rho squared. This might lead to a bounce, perhaps, yes. However, this is a little more exotic, and I don't know actual motivation for this. Yeah, so I can read the question. I don't understand why scalar perturbations delta AX are 0. Can you please explain? Oh, and I just pull up the slide here. It's not that delta AX are 0 in that case. One is considering all of the vector perturbations in that case, which include delta E, this H cross, and delta AX. It's just that one can remove those from the gauge degrees of freedom. So the only propagating mode in the end is HX. So after taking all the constraints and removing the non-propagating modes by their equations of motion, by their constraints, then, oh, you're talking about a different slide. No, which AX are you talking? Oh, here, this one. Let me see, if I recall correctly, I think it's because of the symmetry we're assuming here. We sort of rotated everything. The X and Y directions are behaving the same way in the setup by rotational symmetry. So we've shifted all of the perturbations either in the Y or Z directions. So yeah, and essentially the delta AX behaves as a vector mode in this case, whereas now the Y and Z components can be written here this way as scalar perturbations. Yeah, I'm afraid I can't give some really good intuition for this scalar vector decomposition in anisotropic spacetime. It's a little more complicated than in FRW, but I can provide some references if you're interested.
Okay, so next question is from Professor Nicola Bartolo. You could please unmute yourself and ask, maybe.
Oh, yes, thank you. Oh, sorry. Oh, sorry. Maybe I missed the point, but what about mimetic gravity? Because you mentioned this as another example of limiting curvature, and I didn't understand if for mimetic curvature there are, sorry, yeah, for mimetic gravity there are problems in reaching a similar conclusion. Sorry, maybe I missed the point. Thank you.
Yes. Yes. Thanks for asking. Let me just clarify. So mimetic gravity. Actually, let me pull up here. What I'm showing here is that it's almost the same theory as the Cuscuton. If you replace a mu by minus gram mu phi, you're really having the same Lagrangian, the same theory, except because the mimetic has this additional derivative, nabla mu phi, it implies that you always have an additional degree of freedom. And in the original theory, that was just like the mimetic dark matter. And it turns out that because you have this additional degree of freedom, typically solutions you're looking at will have instabilities in them. Whereas the Cuscuton, you have the gravity, the scalar field is not dynamical, and that's it. If you have nothing else unless you add additional matter. So in particular, in mimetic gravity, you can build non-singular spacetimes, but you always have some instability whereas in the Cuscuton theory, you won't have it. It will be stable.
Okay, so there is a comment from Susmita. She's just saying that references will be helpful, and from Professor Patil was saying thank you. So if there are no more questions, we are running out of time. I would like to thank the speaker for nice talk, as well as all the participants.